Hi everyone. Today we're continuing chapter 18 and we're going to discuss factors that affect whether a reaction is spontaneous. So again, remember last time we talked about spontaneous reactions versus non-spontaneous reactions. And there are two factors that determine whether a reaction is spontaneous, and that is enthalpy change and entropy change of a system. Now, remember from a long time ago, we talked about enthalpy change, or delta H, and that is the difference in the sum of the internal energy of a system and the pressure, volume, work energy of the reactants to the products. So if this is at all rusty, or if it's been a while since you've thought about enthalpy, definitely go back and review those different topics. We talk about thermodynamics in chapter 6, and then we also talk about enthalpy in chapter 11. So feel free to go back and kind of review some of those concepts. And then the entropy change, which we'll label delta S, is the difference in randomness of the reactants compared to the products. So with delta S, we're really thinking about whether there's more order or more disorder in a sense. So remember that the second law of thermodynamics states for any spontaneous process, the entropy of the universe increases. So delta S of the universe should always be greater than 0. So processes that increase the entropy of the universe occur spontaneously. So remember we said that nature is really trending towards dispersal of energy, or more quote-unquote disorder. Some scientists don't like to refer to entropy as disorder. They think it's too basic of a term, I guess you could say. But it is a term that does make sense. When we think about energy dispersing throughout the universe, we really can think of it as, less order in the universe. Entropy is also a state function. So remember from a long time ago, we said state functions only depend on the initial state of a reaction and the final state. So remember, entropy is a state function. So to determine the change in entropy for a system, we're going to take the final entropy state and subtract the initial entropy state. All right, now for a more classical definition of entropy, entropy is a thermodynamic function that increases as the number of energetically equivalent ways of arranging the components increases. So that's a really fancy way of saying that entropy depends on how many different ways we can arrange something. So we're going to give entropy the symbol S. And if you imagine, for instance, a bookshelf, and let's say you have 10 books, and you could arrange those books in many different ways. So maybe you alphabetize the books by author, maybe you alphabetize the books by title, maybe you order them from tallest to shortest. There's a bunch of different ways we could order those books on your bookshelf. So entropy depends on something equivalent to that. How many different ways can you order those textbooks or those books? And entropy is going to increase with the number of different ways that we can arrange those books. So now what if we had 20 books? Now the number of ways that we can order the books increases exponentially, so entropy is going to increase as well. Now, units of entropy are generally in joules per mole Kelvin. So another way of writing that is joules over moles times Kelvin. So that's energy over the amount of whatever we're looking at, and it's also over temperature. All right, so the classical definition for entropy is shown below. So entropy is equal to a constant, K, referred to as the Boltzmann constant, and that's equal to 1.38 times 10 to the 23rd, or negative 23rd, joules per Kelvin. And then we multiply that constant by the natural log of capital W, and that capital W is the number of energetically equivalent ways a system can exist. So this is unitless. And so that W is essentially referring to that example of arranging books. So W would be the number of ways that we could arrange the books on our bookshelf. So that means that entropy is directly related to the number of arrangements that we could have. Now, the scientist who came up with this definition is Ludwig Boltzmann. He was a really interesting scientist. He became a professor of mathematical physics at age 25, which is really young. And one of his students was Svante Arrhenius, if I'm pronouncing that correctly. So previously we talked about the Arrhenius equation, and so that was named after one of Boltzmann's students. And then Boltzmann, he unfortunately suffered from depression his whole life and did die by suicide later on. But his tombstone bears his famous equation. And this is something that is discussed a lot in classes like physical chemistry. Entropy is a really important quantity that we need to know. So we can attribute this all to Boltzmann. So let's talk about that term W, which again refers to the number of energetically equivalent arrangements for a system. All right, so let's say that we have a setup where two round bottom flasks are connected by a tube in the middle. And we can close that path or we can open it. So let's say that initially we start with 4 gas particles, and they're all on the left-hand side of this system. And then let's say we open that valve in the middle, and we let the gas kind of flow through the system. Now, that's what we call state A, where all of the gas particles are on the left. But then once we open that valve, what if all of the particles are on the right? We can call that state B. And then what if the gas particles are evenly distributed throughout the apparatus here? We'll call that state C. Now, these are all energetically equivalent. It's, the energy of the system doesn't really depend on the location of those different gas particles. However, one of those states that we just went over is more probable than the other two. So which one do you think is most probable? So let's find out which one is the most probable state. So state C is the most probable state. Oh. So this is what we would call a microstate. or sorry, this is a macro state, getting my words mixed up. So this macro state can be achieved through several different arrangements of the particles. So what we're going to do is label each of these gas particles. So maybe we'll label them 1, 2, 3, and 4. And you can imagine that maybe instead of 1 and 2 being on the left, maybe they're on the right, and maybe 3 and 4 are on the left. Or maybe 1 and 3 are on the left, and 2 and 4 are on the right, or vice versa. So there's a lot of different combinations we could have. So here are just a few of those combinations. So if we label, again, each particle with a different number, we could have 1 and 2 on the left, and then 3 and 4 on the right. Or maybe 1 and 2 are on the right, and 3 and 4 are on the left. Or maybe 2 and 3 are on the left, and 1 and 4 are on the right, etc. So these are what we call microstates. So these are all of the different arrangements that we could have for state C, which is our macro state. So remember, macro refers to the larger picture, micro refers to a smaller picture. So all of these microstates have the same macro state, but there are 6 different microstates or different arrangements. All right. So statistically speaking, state C is most probable because there are 6 different ways that the gas particles could arrange themselves. Whereas in state A and state B, there's only really one way that all 4 particles can be on one side or the other. All right, so off to the left, we kind of have a summary here of what we just went over. So there's only one possible arrangement that gives state A, and only one possible arrangement that gives state B. However, there are 6 possible arrangements that give state C. So the macro state with the highest entropy also has the greatest dispersal of energy. And because state C has the most microstates, that means it has the most or highest entropy. So it has the greatest dispersal of energy. So how we can summarize that is there is 6 times the probability of having the state C macro state than either state A or state B. So again, what this really comes down to is state C has the highest entropy. It's also the most likely to occur because gases actually fill the space that they're in. So gases would rather be equally distributed rather than just sitting on one side or the other. All right, so let's talk about entropy change that occurs if we have a state change. So for instance, if we go from a gas to a liquid or a liquid to a solid or vice versa. So when materials change state, the number of macrostates it can have changes as well. So the more energetically equivalent arrangements or configurations that the molecules can have, the more macrostates that are possible. So remember, back to our book analogy, the more books we have on our bookshelf, the more ways that we can arrange our books. And so we would have more entropy. And this is true as well if we change states. So we can compare gases to liquids to solids. So gases, for instance, can move around more so than liquids and solids. So gases would have greater macrostates than liquids. Now remember, liquid particles can move around more so than solid particles. So liquids would have greater macrostates than solids. So gases have the most macrostates, or the most entropy, followed by liquids. And then at the bottom here we have solids, which have the least amount of entropy. Because remember, the particles in a solid are all rigidly fixed together, and they're not really moving around. So we could even say that there's only one macrostate for a solid. All right, and then we have the figure down below showing a solid turning into a gas. Oh, sorry, I didn't mean to go ahead. So down at the bottom with the solid, those particles again are rigidly fixed. So they're all stuck together in a fixed situation. And those particles can vibrate a little, but they can't really move around. Whereas if we look at the gas can move, which is called translation. They can also vibrate, and then they can also rotate, so they can flip around in the air. So they have many more possible positions that they can exist in. So those particles have many more arrangements that they can exist in, or more macrostates. So they would have more entropy. And then this is showing that same idea. So this is our heating curve for solids, or for water, excuse me. So starting at the solid, again, this would have the least amount of entropy. So entropy is on the y-axis. And then as temperature increases, we see that the solid will melt. So that's a straight line right here. And then as the solid melts, we're increasing the entropy because now those particles are turning into liquid particles. So they can start to move around each other, which is going to create more arrangements of the particles, or more macrostates. And then eventually we hit the point where the liquid is going to start evaporating. And we have another spike in entropy because now those liquid particles are turning into gas particles. And gas particles can move around even more so than liquid particles. So they're going to have more macrostates or more entropy. Another way that you can kind of summarize this is solids are very ordered. Liquids are a little bit more disordered. And then gases are very disordered. So entropy is increasing from solid to liquid to gas. All right, so let's go over an example. We're going to predict the sign of delta S for each process below. Now remember, as entropy increases, that means that delta S of the universe is increasing. So delta S will be positive for systems that have greater entropy. Okay, so let's start with A. So we have a gas that's turning into a liquid. So is entropy increasing or decreasing? So another way to think of that is the system becoming more ordered or less ordered? So in this situation, because we're going from a gas to a liquid, the system is becoming more ordered. So that means that entropy or disorder is decreasing. So if entropy is decreasing, would delta S be positive or negative? So entropy would be less than 0 or negative. So as the system is becoming more ordered, we're going to see a decrease in entropy. All right, and then B, we have solid carbon dioxide, and it's subliming or sublimes. So we have sublimation occurring. Now, remember, in sublimation, that tells us that a solid is going directly to a gas. And remember that dry ice is CO2. So dry ice goes straight from a solid to a gas. All right, so is the system becoming more ordered or more disordered? And then is entropy increasing or decreasing? So for this particular situation, the system is becoming more disordered. So entropy is increasing. So that means that the sign for entropy for this system would be positive. Okay, now for C, we have 2N2O decomposing into 2N2 and O2. So for this particular reaction, what we're most interested in is how many moles of reactants we have and how many moles of product we have. So on the left-hand side, we have 2 moles. And on the right-hand side, we have 2 plus 1, so that would be a total of 3 moles. Now, the more moles you have, the more disordered the system. So is this system becoming more disordered? Yes. So that means that entropy is increasing. And that means that delta S is positive. Okay. So now we can actually calculate a change in entropy. So on a macroscopic scale, we can define the change in entropy that occurs when a system exchanges a quantity of heat Q with its surroundings at a constant temperature with the following equation. So delta S, or the change in entropy, is equal to the heat that's exchanged, which is reversible, so that's why there's that ReV there, divided by a temperature. Okay. For example, when ice melts at its melting point, the heat exchanged with the surroundings is the enthalpy of fusion. And we can say that that's equal to our reversible heat that's exchanged with the surroundings. So heat can flow back and forth, right? So the heat of fusion here is equal to 6.02 kilojoules per mole. And that's just something we can look up in our textbook. And then the temperature for the melting point is 273 Kelvin. So for 1 mole of ice, we can plug in for delta S the heat of fusion, or QReV, over temperature. Now we're also going to take into account the 1 mole. So we're going to multiply 1 mole by 6.02. And then we could have left that in kilojoules per mole, but entropy is usually expressed in joules per Kelvin. So we're actually going to multiply this by 10 to the third. So remember, if we want to convert from kilojoules to joules, there's 1,000 joules per kilojoule. So that would give us 6.02 times 10 to the third joules. And so we're just going to plug that into our equation. And then we're dividing by 273 Kelvin. And we get 22.1 joules, that should say per Kelvin. Moles will actually cancel, so that won't be in our final units. All right. So let's look at an example from your textbook. We're going to calculate the change in entropy that occurs in the system when 25 grams of water condenses from a gas to a liquid at the normal boiling point of water, which is 100 degrees Celsius. All right. So again, the system here, we're starting with water as a gas, and it's becoming liquid water. So earlier we said that if a system is becoming more ordered, that means that entropy is decreasing. So delta S should be negative. So remember, delta S should be less than 0 for this system. All right, so we just saw that delta S is equal to heat over temperature. And in this particular situation, because we're going from a gas to a liquid, we're going through the process of condensation. So we probably want to find the enthalpy of condensation. However, typically in textbooks, they list a heat of vaporization, right? So that's the opposite process. So condensation and vaporization are reversible processes. So the enthalpy of condensation will equal negative the enthalpy of vaporization, because they're equal but opposite. So if we look up the enthalpy of vaporization for water, that equals 40.7 kilojoules per mole. But I'm going to add a negative sign in front since the heat of condensation is opposite. Okay, so that's going to be the heat that we plug into this equation. So we could also write this as the change in enthalpy for the condensation of water. All right, so let's plug in that 40.7 kilojoules per mole. Oh, but we do need to take into account how many moles we have. Okay, so let's figure out how many moles we have. So at the bottom here, we're told that we have 25 grams of water. So we're going to need the molar mass to figure out the number of moles of water. And let's see, so the molar mass of oxygen is 16, and then the mass of hydrogen is about 1. So our molar mass for H2O will come out to be about 18.02 grams per mole. Okay, so when we do that calculation, we'll end up with a value of 1.39 moles of H2O. Okay, so let's plug that in to our equation. And I'll keep the same color there so you can see where we got that value. And then the temperature is in Celsius, but we want it to be in Kelvin. That's just standard for entropy. So in the denominator, let's add 273.15 to get our value for Kelvin. Okay, so let's simplify this. So we have 40.7 kilojoules per mole times 1.39 moles all over 373.15 Kelvin. Okay, so when we plug that into our calculator, we'll end up with a value of negative 0.152 kilojoules per Kelvin. But remember, we need this in joules per Kelvin because that's standard for entropy. So if we multiply that by 1,000 joules, that will give us negative 152 joules per Kelvin. All right, so that will be the change in entropy when 25 grams of water condenses from a gas to a liquid. And we notice here the sign is negative, which we expected because entropy is decreasing. Okay, so let's work on worksheet problem 2, and this will be the last thing we do for this lecture. Calculate the change in entropy that occurs in the system when 1 mole of diethyl ether, C4H10O, condenses from a gas to a liquid at its normal boiling point. The heat of vaporization of diethyl ether at its boiling point is 26.5 kilojoules per mole. Okay, so in this process, we have a compound called diethyl ether, and it's starting out as a gas and it's becoming a liquid. So this is pretty similar to our last problem. So again, we're going from a more disordered system to a more ordered system. So delta S will be negative. Now, we were given the heat of vaporization, and remember that we really need the heat of condensation because we're going from a gas to a liquid. And in the previous problem, we said that that was equal to the negative heat of vaporization. So the heat of condensation should equal negative 26.5 kilojoules per mole. Okay, so now let's plug that into our expression for the change in entropy. So let's see, we need negative 26.5 kilojoules per mole. And this problem's a little simpler because we're told we only have 1 mole of our compound. And then we're dividing that by the boiling point, but we need it in Kelvin, so we're going to add 273.15. All right, so that will equal, let's simplify here. So the temperature becomes 307.75 Kelvin. And then if we plug that in, we get a value of negative 0.0862 kilojoules per Kelvin. Now again, remember that typical units for entropy are joules per Kelvin. So let's take that value and we need to multiply it by 1,000 to get to joules. So our final change in entropy for this system is negative 86.2 joules per Kelvin. Okay, so I think we're going to stop there today. So again, we discussed entropy, how to predict the sign for a change in entropy, and then also how to actually calculate entropy for a system. All right, so next time we'll start discussing heat transfer for different systems and how that affects entropy. So I will see you then.